other bilateral project in India, Italy.
Yes.
Christoph, no?
Yeah, I wish, okay, Sabu, okay. I wish we would have to the abstract file after this session, this conference finish. Not unpublished, but it's okay. In all the abstract will be the files, and then we can see more detail of the exact address and also to future contact. Because only the abstract, we have no contact address. It's very difficult.
Right.
So ask to the organizer to file to the abstract, which we have sent. All of them is available to enter, to look.
Right.
Okay? Not necessary to publish, but
yes.
of the file. That I would like to ask you. In this case, future cooperation is much easier.
Yeah, I'm making it.
Professor Ilaria?
Yeah.
Dr. Christopher came online. Can you invite?
Christoph?
Professor?
Yeah, okay, perfect. So we can go on with the next speaker, with the next plenary speech, Professor Christoph Nitzer. Are you here? Christoph?
Excuse me?
Yeah, okay.
Yeah, now I'm here. I had just a shutdown of the computer 1 minute ago.
No problem.
I just have to find the file. Just give me one second.
Yeah, no problem. Since I know that I will introduce you, I have just only a very, very brief introduction about you. Professor Christoph Nitzer from Department of Industrial Engineering, Salerno University in Italy. Received the Master Science degree in Electrical Engineering in Germany and also the PhD degree in Germany. After holding postdoctoral position at the École Polytechnique in France from 1993 until 1994 at the Centro Studi e Laboratori Telecomunicazioni in Torino. He became appointed Associate Professor for Optoelectronics in the Electrical Engineering Department of Salerno University in Italy in 1998. Since 2013, he is with the Industrial Engineering Department at the Salerno University in Italy. His research interests are the development of new techniques for semiconductor materials and device characterization, photocatalytics, and thin film electronics based on amorphous semiconductor, polymers, and carbon nanotubes. He's author and co-author of more than 130 publications in international journals and proceeding of international conference, and also 4 Italian and 3 international patents. So it's really a big pleasure for me to introduce you. If you can share your screen.
Yeah, I try. Let me.
The title of your plenary speech is Matrix Influence on the Sensing Properties of Carbon Nanotube Network-Based Room Temperature and IR Sensitive Bolometers.
Yeah, just a moment. I asked for the condition. I hope it's working.
No problem.
Silent.
Let me know when it's
At the moment, no.
Maybe I tried. Also yesterday I had some problems the first time, and the second time it was working.
Did you send your PPT? Did you send your file in order to share?
Not yet. So
No.
just I tried again. No?
Yeah. If we have some problems, you can send us the PDF file or PPT file, and we can share it for you.
Just I try again, because yesterday it was the same. It worked finally. No?
You have to share the full screen.
Yeah, I did. I asked for it. Now it should go on. Do you see it now?
No, we can't see. Oh, now yes. Finally,
Okay.
yes.
Yeah, it is.
Yeah. We can see it.
Yeah, unfortunately, the computer went down just some
Can you
minutes
make
ago.
full screen?
Some
Yes,
screen?
full screen.
full screen.
Yeah,
Fine
good,
now?
good.
Okay.
And also Nasco, if you can, you.
Yeah.
Okay, you can
Maybe
start.
I should put down the volume. Otherwise, I found this morning it gets always into some problems. No?
Okay, thank you.
Okay. That's okay now. Yeah.
Yeah, it's okay. You can start. Thank you.
Yeah. Okay. Good afternoon or good evening here. It's noon in Italy. No? In Kerala. I'm sorry that I cannot come. I would really like. I have been twice or three times in Kerala, and I appreciate it very much. I will speak about the matrix influence on the sensing properties of carbon nanotube network-based room temperature near-infrared sensitive bolometers. So we will use the same nanotubes and then change the matrix. And I'm come from Salerno University and from the Department of Industrial Engineering. Actually, I'm an electrical engineer. Just let me show just one thing. Salerno is close to Naples in the south of Italy. I want to show you, this is our, on the left side, you see our sign, and it's a very old university actually. It's the oldest Italian university, by the way. No? And it was a medical school more than 1,000 years ago, and it has been refounded after World War II. Now it's a big campus. We have about 40,000 students. No? And recently we have a very nice, 2 megawatt solar panel installation. Not recently, that's 20 years ago also. And I remember that you also at Cochin Airport, you have something very impressive also in this direction. No? So it's becoming a green university. Besides, you see, we have some green in between. No? Outline, what I want to show you today is that preparation and sensing properties, in particular of symbiotic polystyrene, multi-wall carbon nanotube composite samples. No? And a lot of we'll speak about electrical characterization, electrothermal characterization and light sensing characterization, so optoelectronics and electrothermal measurements. No? And as you will see, a lot goes about the improvement and stabilization of the sample electrical and sensing characteristics by Joule heating. This is not the only, burn-in procedure I will show you. Electrical characteristics are very sensitive and have sometimes to be stabilized. This is one of the central arguments. No? Then I will show how you can use it. If you have a nice temperature sense, of course, you can do light sensor by bolometer application. And I will show this here mostly for near-infrared light sensing. No? Then after the central will be on symbiotic polystyrene multi-wall carbon nanotubes. I will compare it to epoxy multi-wall carbon nanotubes and high-density polyethylene multi-wall carbon nanotubes. Always the same commercial nanotubes. And then in the end, I will compare it to a new system. We had a collaboration with a biologist in our department and we made it transparent. No, first I had a collaboration with an Indian PhD student who worked between Russia, Estonia, and Finland, and we got a single wall carbon nanotube network without matrix, and we compared to bio-nano composites, where we did samples either with plant or fungal cells. No? Okay. Carbon nanotubes influence strongly the optical characteristics, and when added in a quantity above the percolation, of course, the mechanical and electrical characteristics extremely, in orders of magnitude. No? Polymers with incorporated network can be used as sensor. We had a lot of examples today, no? And I will show you just temperature, moisture, and as actuator in this kind, heating and de-icing, for example. No? Polystyrene has an advantage that it does not incorporate water in comparison to the polyethylene or to epoxy, for example. No? The polymer structure, the CNT network electrical interconnections and metal contact carbon nanotube electrical interconnections can be changed by heating. No? So they are, if you make a heater, you may change them during operation, or you have a sensor as well. So you have to stabilize them in some way. No? Internal heat sources is often more effective than external heat source for sample modification. No? Mm-hmm. You can use this even for crystallization. You can use the nanotube conduction for example, the preparation of an epoxy nanotube of the curing procedure. You can cure it by Joule heating. No? The used material were in this kind symbiotic polystyrene, just a commercial one with a molecular weight of 320,000 gram per mole, and symbiotic trials more than 98%, and multi-wall carbon nanotube standard, very it's already standard since a long time. Multi-wall carbon nanotube from NanoSeal with about an average diameter of about 10 nanometer and a length ranging from 0.1 to 10 micrometer. No? Not with extra purity, no enhancement or something else, just the less expensive carbon nanotubes we can get. No? You see here below, you see on the left side a single carbon nanotube. On the right side, you see that is because Italians like carbon nanotubes. It looks like spaghetti, actually. No? So it's a network of the carbon nanotubes. No? Okay, the sample preparation was an extruder and carbon nanotube polymer were premixed, loaded into a compounder. Then it was processed at 295 degrees and extruded. No? The samples were extruded and then cooled down to room temperature, and it was then molded in a hot press. And there were 100 millimeter about thick films. No, 100 millimeter, yeah, and which were then quenched and prepared in a special. 100 millimeter is a little bit. That is an error. No? Finally, we prepared gold evaporation electrical contacts. No? So here you see, for example, one of the influences. There are a lot of structural characterization. I will not show you. I will concentrate on electrical characterization. No? So you see on the left side, for example, how the X-ray diffractograms change with nanotube concentration, and you see actually that the material becomes more crystalline, no? With this light like a threshold value, and then it stays constant. We prepared different concentrations, and here for the application, we will show you just the highest loaded sample with 9% carbon nanotubes. No? Okay, this is the sample. This is about 2 centimeters. It's a large sample, and we have evaporated on gold electrodes. The gold electrodes, of course, why gold in this case? I will show you. We made a work before where we changed all kinds of electrical of metallization And it's very critical. So it's not only if you want to have a very stable electrical characterization, contacts is always one of the most critical problems. No? If you do this, you have here a perfect linear resistor. If you don't exceed too much with this, with the voltage, otherwise you have self-heating and it becomes a little bit nonlinear. You see the correlation is 1, is perfect. No? And it's a linear resistor. You see we have 6 at 5 milliampere about and 1 volt. So that means 200 ohm. Extremely stable resistors. No, the 2-point measurement geometry is okay. We don't need the 4-point. We had this possibility also. No, and okay, I said we had these. No, it's not 2. It's 4 centimeter distant electrodes. No? So now what changed? We start to change the voltage. This was up to 1 volt. No? Now we go up. We go on these characteristics here, and you see something is happening at 26 volt. It looks like a breakdown, no? in the characteristics. Fortunately, we had limited the current to about 100 milliampere. So that means we have a cycle that goes like this, goes to this way, comes back, and then it goes back this way. And afterwards, we could continue. We always have these characteristics, no? Within plus minus 10 volt, and we didn't go anymore to 25 volt. So we applied in the beginning a very high power, electrical power, which was too much for this resistor. In this way, it modified, but it modified in a positive way. I said it was breakdown, but it enhanced the conductivity. This is before Joule heating. This is after Joule heating. And you see, it's perfect again. And this is up to 10 volts. And we can measure this very often. So we had a kind of 60-fold increase of conductivity. We have a good homogeneity. We measure with an infrared camera the heating. If we go for a 50 volt, for a 10 volt, for example, where now we have 10 volt, we have about 500 milliwatt. No? It's a nice heating heater. No? Okay, what we see now, we want to see, can we use it as a temperature sensor? So we made temperature cycling. Normally we heat about 1 hour and we let it cool it 3 hours. No? So then during the cooling period, we are in equilibrium with the sensor. This is measured by a thermal element, and this is measured. This is the current of our sample. And we know it has exactly the same temperature in the slow cooling range, not in the heating range. No? So normally we take data of the slow cooling, and you see before we have even some noise here. We have some maybe non-linear, non-monotonicity. We have some, but we have already almost monotonic behavior. So we could see it is a temperature sensor. After the Joule heating, it becomes much more clear and much less noisy. I told you now we have here's 1 volt, here's 5 volt applied. We have a much higher current, no? And it's a NTC resistant. And that is before heating, the relation between temperature and resistance, no? Now the current, so that is the conductivity. And you see it becomes almost linear, no? And it's nice characteristics, no? The coefficient is not very high. That is, you have to see, no? So if we want to use it as a temperature sensor, we need a very stable measurement in some way, no? So what happens now when we illuminate? We wanted to use this sample, and we use a 1300 nanometer low intensity, below 5 milliwatt, normally LED diode, no laser, no high intensity light. And you see, we switch on the current. We have some changes of the resistance. This is the resistance. This is the normalized resistance due to Joule heating in the beginning. At this, it's just 1 volt. We have still some heating. No? Then we switch on the light. No? We switch off the light. We switch on the light. We switch on 3 times, and we see nice modulation of the signal due to this wavelength, 1300 nanometer wavelength. This is already out of scope of silicon, because silicon goes up to 1100 nanometer. Okay, so we have a bolometer, and then we have a drift. Actually, this is the change in the temperature of my laboratory. It was Friday evening. It was a Friday evening experiment, and they switched off the power, the conditioning system. Okay, now we did the same again, and I show you again. We look for reproducibility. We changed now to 780 nanometers, and we measured in the same time again the temperature. Here we took a part where we had a dip in the temperature, in the ambient temperature, and we see in the baseline of our electrical signal the same, of course, but we see the amplitude is not changing. So we see a very nice light-induced system. If you do two of these, we will make a zoom. You see this time scale, and 100 seconds of light, seconds of light pulses, and we see about the same rise and fall time. It is no residual. It's a nice light sensor. It's slow because it's a big sample. Simply, we could make it faster, making it smaller. And again, now I took away here the peaks, and if you take them away, you have again the characteristics like before. It doesn't look so nice because it's not so easy to take away the peaks. But you see again the sensitivity, the temperature coefficient of this resistor. Okay, what we can see, multiple carbon nanotube polystyrene composite can be mixed homogeneously, and this addition favors polymer crystallinity. Joule heating by applied high voltage can improve the electrical conductivity, the long-term stability, and the linearity of the electrical characteristics. We had a stable linear temperature sensor, only, you have to say, only in a limited temperature range, about 50, 60 degrees. But bolometer operation at 780 and 1300 nanometer had been shown with a very good signal-to-noise ratio, that even if the temperature coefficient is very low, that is due to the excellent stability of the electrical characterization. So now we go to the next system, and it's epoxy. It's a epoxy, normal epoxy ether with bisphenol A, and it's cured, and we get nanocomposites. Now we get a very highly conducting material. If you see here, this is the conductivity in function of the nanotube content. Already at 0.5, this is the 0.05. We have a very, we are above threshold. So that means we have a much higher, much better conductivity for the same content of carbon nanotubes. This is a material which is stable not until 50 degrees, until 200 degrees. And again, it's very it's extremely stable. You see these after has grown, and then after 37 days in ambient, for example, no change can be seen. It's a very stable system. But epoxy takes on water. So what happens? We immersed it in water. A lot of times we measured by measuring the just weight, the water content, and the water content went up to 3.5%. And you see, this is the on-take of water content, and we see the change in resistivity, and the resistivity with water content increases linearly almost. So that means we have a kind of the material is swelling. That means the resistance is determined mainly by the tunneling resistance between nanotubes, not by the nanotube resistance itself, but the interconnection resistance. And by swelling, we change this. So you have a nice humidity sensor. It's a humidity sensor sensing its own humidity, actually. And this is if we do it for a long time in laboratory atmosphere. We see also uptake of water until it saturates. And we can even see, we saw then change of ambient, but it's very slow because it's a very big sample. So that's a chance for humidity sensing, but hence epoxy is a poor temperature sensor. Polystyrene does not incorporate water. Polystyrene is a pure temperature sensor, just pure and pure, because it does not take on humidity. That is now what you can do with the epoxy. Here we heat it. We apply 1 volt, it's constant. Then we apply 140 volt, and we get 140 degrees by chance. It's the same 1-to-1 relation. Then we measure, we apply again 1 volt, and we measure the resistivity, and we see the cooling. No? We see the cooling transient. It goes back to the same value, but now we use the properties of it's also almost linear, temperature dependent, but it's temperature and humidity dependent. No? Here you see the infrared temperature measured, and that is the current. It's linear actually. No? What if we use it as a bolometer? So we see again it's slow in some way because it's a very big sample. That's the only reason here was the biggest sample from dimensions. We have a change in the baseline. And at 1300 nanometers here, we have something like accumulation. That means something is changing. And what we think is maybe with illumination that is perpetrating, going into the sample, we change the humidity. No? If we change the humidity, we change the resistance. No? It's a very small change, if you see. No? But it's again the humidity sensor indirectly by the baseline. No? And you see it's not so good bolometer. No? Okay, next one is polyethylene carbon nanotube composites. And there we compared high density, low density composite long time ago. And you see you can again change about 12 orders of magnitude, the conductivity. No? Low density, high density in the threshold is not so different. It's very different in some other, but I will not go into details. And here I show just the bolometric response of 400 nanometers, 780 nanometer, 1515 and 1720 nanometers. So we go from the UV, the border of the visible UV, to again the infrared at 780. And you see here we have 3 milliampere, 30 milliampere. So we change the intensity. We have quite a good dynamics on that. No? And 1550 and 1700 starts to become noisy. No? That's maybe a problem. No? But in some range, we get an acceptable bolometer. No? Here again, you see, here we see something which we often find with carbon nanotubes. You see spontaneous changes like random telegraph noise. You see addition, how many, you have a lot of concentration, but you don't have a lot of percolation paths. Maybe you have 50 percolation paths or so, or 20. And then if one of them is changing, is attacking or not, you see switching by discrete steps. No? So that is the problem here in this kind of device, which we didn't find for the polystyrene. And here we change now the intensity of the light just by changing the current of the LED, no? 5, 10 until 30 milliampere going down to 1. And here you see even we still have kind of a dynamics which is interesting, but it's a little bit noisy. No? That is like kind of following, maybe because of temperature. No? This is the alternative to the carbon nanotube with polymers or epoxy, and it's a pure single-wall carbon nanotube network. This is a very nice network, I have to say, and we got it. I got it from the PhD student. He now finished. He went back to India as far as I know. No, and he got this from Skoltech in Russia. And you see, we have these were we actually wanted to use them for another reason. This is almost perfect transparent conductive oxide for solar cells. No? So he made a solar cell just without evaporation, just putting this device and putting it on it. He made a kind of record efficiency for this kind of solar cells with these simple networks, very nice networks. Again, you can use them as heater. That's transparent. That is 90% transparent, by the way. No? So, and you see, it's a bolometer, but it suffers in some way also from cycle stability. And that is why people want to use matrices can stabilize, because now carbon nanotubes alone, of course, they are sensors in all way. You have adhesion, you can use them as gas sensors. Everything is changing the conductivity. So better in some way to put them into an encapsulating matrix. So just the last I'll show, we use not only classical matrices, we use bio-nanotissues. We made bio-nanotissues by combining carbon nanotubes with biological cells, mixed them. Then they were combined in some way. The receipt you can find in this publication here from about 10 years ago. We dried it, and then we made again electrical contacts or mechanical contacts. We wanted to measure the mechanical properties and the electrical properties of these new kind of bio-nanotissue. Here, just we had fungal plants for tobacco, fungal were candida in this way. And here you say with 20% multi-wall carbon nanotubes, always the same carbon nanotubes I showed you in the beginning, in all this work, besides the single wall nanotubes from Scholtech. And you see here, you have big cells and you have nanotube networks around, and they have to form a percolation network in some way for electrical conduction. So that's what it looks like if carbon nanotubes grow on these were living cells in the beginning, and even then we measured them. Okay, let me show the results for Candida was the first. With Candida, we could then heat it and it was stable. If you see, this is temperature and this is the conductivity, and you see it's linear, again, you have again we found it's not very conductive. It's a microampere in this way, 100 less than a milliampere for 1 volt. But it's conductive, and you see change in the electrical characteristics. And that is the transparency. This was 40% transparent. Here you see it. You can fold it. It's a bio-nanotissue which is foldable. And it's transparent, a lot of interest, and you can use it even as a temperature sensor up to high temperatures. Then the next one what we used was made of tobacco. Here you see the sample. Again, it looks very black. It has some transparency. Nevertheless, about 4% or so. It was a thick sample of 100 micrometer with gold contact, standard, big sample. And we measure first electrical characteristics. Here it's at 75 volt, 6 milliampere per centimeter square. So you see, no, it's not volt, which that is the current density and electric field. So it's conducting. It's not good as a heater. It's not high enough the conductance for that. We measure the electrical characteristics, AC characteristics, where then we can calculate the elements of the AC circuit, and we measured strain, mechanical characteristics, and this has quite interesting, very good mechanical characteristics. Okay, what we did now, or what did my PhD student actually, he didn't like it and he didn't understand in the beginning what was happening. That is before current voltage characteristics, not extremely linear. Now he implied that it's 150 degrees and volt and 70 microamperes. That means we have a 2 mega ohm resistance, and not even linear. It's not enough for heating. What is it good for? It's not easy to say. That is what happened then. The current went down. Then you see steps. It went down and went down to a much lower value. And if you see what is happening afterwards, here you see then it went down to 3 microampere instead of 70 microampere. And it's still moving. But we don't see steps. That is interesting to see. Here we see steps. So that is what we expect from carbon nanotube. Here we don't see steps anymore. So what I would say is probably we destroyed by extremely high current densities all percolation paths. There is no percolation path anymore, but we have carbon nanotubes which are very close. they make a gap. They will make a very small gap, and that gap can be used for sensing. What I show you now, this is for lower voltage. We see it's linear. It's a very high ohm resistor. This is a giga ohm resistor. No, it's a 3 giga ohm resistor. Very difficult to even this is interesting application. No, and we illuminate it with 19 microvolt but at 1300 nanometer light, and you see the very small slight change of the impedancy. We can see it here. No, so we have a light-dependent resistor. No, if we have a light-dependent resistor, we have a bolometer, and what you see here is this is 780 nanometer bolometer operation. We see here noise. We see dark noise, of course. No. And but we see a very good signal-to-noise ratio. And what you see is here, this is a very low-intensity light, no? And you see we have 3 nanoampere of background, and we have about 0.3 nanoampere of 3 nanoampere of modulation, no? And if we look, it's linear. We change the intensity, and the change in the current in picoampere here is linear. Huh? We have a linear photoreceiver. No? Here it's just a thing. We have a simple LED, no? Low intensity LED. No? But we get even with this as a simple application now a very high modulation, no? Much higher than in the other cases. Here we do the same now for overnight, where we measure the temperature and the current. You see the current is constant. Now it is modulation. That is, if you zoom in, that is the dark current in the night. It changes. No? So we have a temperature sensor. In the night, the temperature changes. No? The dark current is changing, but the modulation changes much less. No? If we plot the temperature versus dark current, we get here linear characteristics, and we get an NTC coefficient of 23.7% per Kelvin. This is almost record for the temperature sensor. No? And you see how is the amplitude changing with cycling time, this whole night. No? You see it's changing a little bit. No? So we see a modulation. We don't have perfect stability of the intensity, but it's not jumping. It's kind of there's a little change. The change should be due to some characteristics of the gap. No, here we measure the temperature with an infrared thermometer without and with illumination, and actually we see that the change is just 0.1 degree, and here is 0.3 degree, no? For 1300 nanometer as before, and here is for 780 nanometer. So it's 0.3 degree, and you see very nice signal for this 0.3 degree. No? Okay, what can we say? Low-cost polymer epoxy multiple carbon nanotube composites are attractive for actuating and sensing. They can sense temperature and humidity. I would say because all sensors should be specific to one would be nice. They are specific to two, of course. No? When their electrical characteristic has been stabilized, right contacts and right burn-in procedure, all investigated systems can be used as bolometers, achieving very good signal-to-noise ratio, even when only minimal resistance changes are obtained by low-power LED illumination. No? Syntactic polystyrene as multiple is particularly interesting because not suffering from humidity. No? So you don't have changes imposed by the light itself. No? By external ambient temperature, yes, but not by the light itself, if it's low intensity light. Bio-nano composites are interesting new materials for temperature and light sensors with high sensitivity and good long-term stability. Good long-term, we remeasured them after 5 years, and they were still stable working. And without the nanotubes, the cells would just be dust. No? So we could make a stable bio-nano tissue, which has optimal sensing characteristics. For the tobacco nanotube, I have to say we have to stay very close to room temperature. We cannot go to 50 degrees already. It starts 40 degrees is okay. It's like living organism. No? You shouldn't go over 42 degrees. Then we end up not only in the hospital. No? Therefore, this one, what is happening then? The humidity is important for the sensing, and it's also extremely dependent on humidity. This we found out. I didn't show here. No? Thank you very much. First acknowledgement. This is our collaborators all from Salerno University, mostly just one from my department, or two. And the rest are mechanical engineers, a lot are chemical engineers and biologists, no? And so it's a big group. We have everything around, no? Two colleagues from University of Berlin, where we had very nice imaging, no? And Andrea Sorrentino from Lecco for the sample, the samples of the polystyrene, for example, and the collaboration with George Simon from Monash University for the high-density polyethylene, no? And low-density. Well, just to think, thank you very much for your interest, and continue to enjoy your nice environment. I'm envious, no? Because I had been there in Mona and in the T region. I had been on one of these ships close to Kottayam. I have been in the temple here, so I have to come back in some way. And you have a lot of churches, temples, everything, mosques. I went. You have also in Cochin. You have a synagogue. You have all kind of interesting architecture. No? In Italy, this is close to my place. We have volcanoes, dangerous. This is Vesuvius. We have also water. We have a coast. It's a Amalfit coast. No? And we have also temples. Our temples, the nicest ones are Greek ones, actually. We have a lot of temples of all kinds, but I say the nicest ones we have is Greek. No? Okay, thank you very much for your patience. No?
Thank you, Christoph, for your nice presentation about these innovative materials with carbon nanomaterials, but particularly regarding the bio-nano composite that you proposed at the end of this presentation that are very innovative. I have just only a curiosity. According to you, it's possible to use instead of carbon nanotubes other kinds of carbon nanomaterials, for example, carbon black or graphene or other things?
Yeah, actually, in the beginning, I did not want to work on the graphene because too many people, but we worked also on graphene. We didn't use it. We used it for other purposes. We did batteries. We did non-ambient-friendly batteries, for example, by graphene oxide. No? And then with the carbon black we used, and what we got a temperature-independent resistor, no? A very thin film, which was polyimide with carbon black, and it had no temperature coefficient. No? That is, normally people do some effort to do this with sandwich systems or so, but it was completely without, and it was heating very, very strongly. No? It was a very good heater. We put it on a glass, and it was a thin film. No? And when we made a transient of electrical current, we broke the glass. No? So just to say, so we worked a little bit with other fillers, no? But the main work, I didn't show you. I'm an electrical engineer, and a lot of work, what we worked on was to understand the mechanism of interconnection between the nanotubes. No? And we used a new technique, which is noise spectroscopy. We used electrical noise to understand the interconnection. No? That was, you can use the noise as a signal also for sensors. That's another very nice feature of that. No? But as I told you, I would say we stayed more with carbon nanotubes. No? We touched the graphene more for battery operation. No? And you know, of course, graphene is ideal for what I showed you, the nanotube network for the solar cells. No? And that's my field actually is photovoltaics, my original field. No? So in this way, you can do this even better with graphene, no? With a graphene, large graphene sheets, which you put just on top of the solar cell. No? And the strange thing with graphene is they lost almost the application where you got the Nobel Prize for. No? Not so many people do graphene transistors anymore. The transistors, the carbon nanotubes definitely won. No? You have carbon nanotube transistors rivaling microelectronics, the best microelectronics devices. So that's just to tell you how I see. I see maybe a lot, graphene has a lot of application, but in sensing, of course.
Okay, thank you.
Infinite almost. No? Nanotubes has the nice thing with anisotropy. You can play with this, you can order them, you can attach to special points. As we saw before, we saw a very nice biological sensor before, no, a gas sensor. No? For example.
Okay, thank you, Christoph. Now, Professor Murugatas has a question for you.
Yeah.
And
Yes.
I imagine Professor Thomas later.
Okay, now
Yeah.
I see you anymore. Yeah. Professor.
Thank you. Yeah. So as Professor Christoph said, the CNT network is a unique semiconducting material when you compare to graphene or something else. So in our recent research, we found that in the CNT network, the crossings between two CNTs makes the hotspot. Actually, that is the difference between a continuous graphene sheet and a sheet of randomly arranged carbon nanotube network. So we found really extremely high switchability in these CNT networks, as Professor suggested. We got about 10 to the power 7 on-off ratio, and those were due to the crossings, the band mismatch crossings. So I think that is the for us, in the perspectives of field effect transistors, we are working on thin film field effect transistors made up of randomly oriented carbon nanotubes. So those were extremely switchable. Actually, we would say hotspots, sensing hotspots. Yeah. So that makes it completely different from graphene, a continuous graphene sheet.
Yeah, that's right. For the CNT network transistors, I favor this one. It's easy to make them reproducible. No, you can make P and N. You can. First people made a carbon nanotube computer in Stanford some years ago already. No, complete computer. No? So I think the memory they did not make. You can make memory, of course, but not so reproducible. No, so far.
Yeah. Also, the metallic semiconducting also possible. Not only P, N, and it's M and S also possible.
Yeah, you change the doping type just by changing the gate isolator. No, in this case, it's hafnium oxide, aluminum oxide, for example. That was one of the possibilities. No? Yeah. So I'm also a big fan of carbon nanotubes. No, in this way. So thank you for helping me. No.
Very short question. Very impressive talk, actually. Very impressive talk. You have covered a variety of polymeric matrices. You know, my question, you know, Christoph, when you incorporate these nanomaterials, you always achieve very good dispersion. Then only it can act as a good sensor, right?
Yeah.
Dispersion, and you could get a good network at low percolation threshold, or is it a mandatory requirement that you should get excellent dispersion, right?
You can, if you look for the SEM pictures, you get good dispersion. But then I can tell you some very interesting things. If you do thermal cycling and you, for example, you take high density polyethylene, you heat it over a point and you get crystallized, very crystallized sample, you lose the conductivity. No? That means the matrix, even with a very high concentration and good dispersion, you can, with the local matrix interplay, you can destroy completely the conductivity. No? That That is one thing. If you cycle, for example, high density polyethylene and low density polyethylene, they compare completely different, no? Even if the initial value is similar. But if we exceed over 120 or 130 degree, we lose the conductivity even with highly charged material. No, so it's a very complicated interplay with the matrix. No, I think you need it for some stabilization, but it's very complicated. No,
right. And your epoxy system, epoxy carbon nanotube system, when you have a moisture, ingression, moisture, when water molecules diffuses into the material, you have a linear decrease of conductivity, or always you have a...
with increasing moisture, you have a swelling, and with the swelling, the carbon nanotubes at the connections, they have higher distance or saying
right? The connectivity is affected, right?
Is affected. That's right.
Okay, I understood.
It's affected, but you could use this as a moisture sensor, for example, for airplanes. No? You could use it for de-icing, but you can also use it for revealing the epoxy content.
Right. Yeah,
but with epoxy, it works up to 200 degrees. It's a perfect heater, no? Very good heater with self temperature sensing, no? And self humidity and sensing. No? But if you heat it, then it's zero humidity. Then it's good, an optimal temperature sensor. No? Yeah.
Yes. Thank you. Very good talk. Thank you.
Yeah, thank you.
Any further questions from the participant? Probably no. Thank you for another time for your wonderful presentation. So I think that we can close this session, this plenary session, and I think that now I'll give the word to Professor Thomas.
We have one more job.
Now there is the horizon. Horizon Europe, no? Thomas Purser. For me, it's not possible to hear.
Yes, I think he's muted.
Yeah.
Hello, Ilaria, ma'am, is it audible? Hello, ma'am.
What?
Is it audible? The video is audible for you, for everyone?
I cannot hear anything.
No.
No, please fine. So now it is audible to everyone.
No. It's very, very... Probably you have to increase the volume.
So
Hi, and greeting.
hello, Dr. Ilaria. Is that video audible to everyone?
At the moment, no.
So it is loading. Please
This
wait.
is Tom Webster, and I'd like to thank
Now it's running.
Now, yes. Now, yes.
conference
Yes.
organizers for this
So
invitation
I have to introduce
to give a plenary talk on what we have been doing, I guess, over the past 25 years. And in particular, what I want to emphasize in this talk is our efforts to commercialize nanomedicine. So I do want to mention I'm no longer at Northeastern University. I left that university to pursue more ambitious goals of commercializing our research. Some activities I was not able to do while being an academic professor at Northeastern University. So having said that, I definitely need to give some disclosures. For my presentation, I'll be talking about research that spun out of my lab into companies, Audex Medical, Interstellar Therapeutics, and a company called NanoV in particular throughout this presentation. So, of course, what I would like to start off talking about is COVID. And I know we're all sick and tired of hearing about COVID, but I apologize. I want to highlight what has gone wrong, what went wrong in our global healthcare system that really led us to a point where everything closed down. And many times those of us in the healthcare field, whether it's biomaterials, drug delivery, pharmaceuticals, whatever your particular area of healthcare is, we have been talking about problems in our healthcare system for decades. And this was even before COVID-19. And I don't think I'm saying anything all that provocative when I say that our global healthcare system failed us during COVID-19. I think anytime that your solution to stopping a global healthcare problem is to tell people to stay home, tell people to stop traveling, to tell people to stop interacting with others, we have a problem in our global healthcare system. But I want to highlight other reasons that I think we have problems in our global healthcare system. And this was before COVID-19. COVID-19 simply exacerbated, highlighted some of the problems in our global healthcare system. And we've been talking about these for years. Overcrowded hospitals, barriers to entering a hospital, whether it's economical barriers, geographical barriers, or even psychological barriers. There have been a number of wonderful studies highlighting that depending on your age, depending on whether you're a male or female, depending on your culture, whether you're more likely to go see healthcare or not. And I think we've learned through COVID that something that affects one of us in our healthcare system can end up affecting all of us. So we certainly have a lot of barriers to entering a hospital or doctor's office. We have medical devices that fail, despite the fact that hip implants, pacemakers have certainly helped the lives of millions. There are still functional lifetime efficacy problems with these implants. We have an overdependency on drugs to think that that'll fix all of our problems. All I have to say to you is antibiotic resistant bacteria, and you'll be able to understand the problems that antibiotics have created. Yes, they've solved problems, but they've also created problems. We have to get our healthcare system away from this idea that drugs can solve everything. We tend to treat every patient the same in our healthcare system, yet we have slightly different immune systems. We might have different reasons for receiving an implant, but yet we end up receiving the same implant. We have reactionary versus what I think we need to move towards, predictive healthcare systems. Every other aspect in our society predicts problems before they occur, like building constructs and the strength of bridges. We try to predict when they're going to fail. In healthcare, we do a very poor job of predicting healthcare problems. And of course, all of this inefficiency in our healthcare system leads to increasing costs. We have an increasing global population, so these inefficiencies will only be highlighted more, as was done with our COVID-19 pandemic, highlighting these problems that we have in our global healthcare system. So many years ago, my personal story is 25 years ago, we turned to nanomedicine for some answers. And the field has grown so much since the middle 1990s when we started looking at nanoparticles, nanotextured surfaces, nanotubes, self-assembled nanomaterials. All of these are different categories of nanomedicine. And I'm so happy to see that the field has grown so much. And what it has grown into is solving some of our current medical problems. What I'll tell you during this talk are that nanomaterials have been approved by regulatory agencies like the FDA here in the US to treat human problems, human health problems. We have a long way to go, but we've already created solutions. So I want to highlight what are some of those solutions that we've created to helping us get through COVID-19. And many people don't think about this, but there are many nanotechnology, nanomaterial solutions that have been helping us get through COVID-19. If you think of prevention, nanoparticles can now be found in masks. And these nanoparticles, mostly metal oxides, like silver oxide, zinc oxide, copper oxide, they secrete reactive oxygen species when they get wet to kill a virus. So if you cough and you're wearing a mask, of course, it's wonderful that that mask can trap the virus to keep it from spreading and infecting somebody else. But what's even more wonderful is that putting nanoparticles in these masks can kill the virus if you cough and the virus comes out in phlegm or some mucus. So we have seen many people commercially use nanoparticles in masks that are helping to passivate, kill the virus, in addition to keep it from spreading. We've also seen a lot of technologies where you can coat everyday surfaces with things like selenium, iron, silver, nanoparticles. And these nanoparticles not only can inhibit viruses from attaching, keeping them from spreading from patient to patient, but again, they can release reactive oxygen species. They can be activated through UV light to release active reactive oxygen species, which again, can kill SARS-CoV-2, the virus that causes COVID. And here's a picture of some of the work from my lab in which we've taken aluminum, spray coated it with nanoparticles of selenium, where we can reduce, inhibit SARS-CoV-2 attachment. So everyday surfaces have been coated with nanoparticles. We've also seen nanotechnology help us in terms of diagnosing whether you have COVID-19, whether you have SARS-CoV-2 in your body. So things like magnetic iron oxide nanoparticles have been functionalized with regions that attach to SARS-CoV-2, and then you apply a magnetic field and you can concentrate that virus. So now you're able to detect very small quantities of a virus in a solution using magnetic nanoparticles. But another area that we've been involved in, that I've been involved in, is therapy. And of course, you can think of vaccines, which nanotechnology is being used in today's vaccines, which I'll get to. But you can also think of therapies where self-assembled materials can attach to SARS-CoV-2, keep it from attaching to a mammalian cell, entering that mammalian cell, and replicating. So here's a quick video of how we are using self-assembled nanomaterials and nanotechnology to passivate SARS-CoV-2.
The self-assembled nanomolecule can attach to the virus surface protein. This would keep the virus from attaching to a cell, entering the cell, and replicating.
So obviously, as you can see from this oversimplistic video, we are creating self-assembled materials that have peptides that can attach to regions of SARS-CoV-2, block it from entering a cell, therefore blocking it from replicating and allowing your body to naturally remove the virus. Many people have used this approach. Here is our specific chemistry that we've been using to passivate SARS-CoV-2. And what I want to highlight is we leveraged our research in self-assembled tissue engineering materials to create this self-assembled SARS-CoV-2 passivating material. We took over a decade of knowledge that we had in this one particular self-assembled material that we used to regenerate bone, regenerate cartilage, changed it slightly to attach to SARS-CoV-2 and passivate it. So although I was never an expert in viruses, I was never an expert in virology, I was an expert, and hopefully still am, in tissue engineering. So when SARS-CoV-2 emerged around 2019, 2020, we wanted to contribute. We thought it was our job as scientists to contribute to this growing pandemic. Unfortunately, at that time, my university did not allow me to do work with SARS-CoV-2, so I left and basically started a company who is now commercializing this approach. And I'm very happy to share these results with you. Here is the molecule that we developed. It's called, again, a self-assembled nanomaterial. It's composed of 2 DNA base pairs, guanine and cytosine. And as you know, DNA has a self-assembled property through hydrogen bonds, both self-assembling in the XY direction and in the Z direction through these hydrogen bonds and secondary bonds. We took this molecule, and again, we transformed it from a molecule that could improve tissue growth to one that could attach to the virus, blanket the virus, cover the virus, and keep it from entering a mammalian cell to replicate. This particular version is our tissue engineering self-assembled material. And you will see here again are the 2 DNA base pairs, guanine and cytosine. We functionalize these with lysine. As many people know, lysine is an amino acid that promotes anchorage cell attachment and growth, like bone cells, chondrocytes. So again, this is the material we took. We simply replaced this lysine group with another peptide so that instead of promoting bone growth, cartilage growth, it would attach to the virus. So here's some of our prior work over, again, 10 years of work showing that these materials are safe in the body. They reduce inflammation, promote tissue growth. Here's a study where we injected this into a bone defect. On the top, you can see the control, no implant. After 12 weeks, bone growth did not occur. When we inject this into that same defect site, we call this material Arxis, the trade name. You can see increased bone growth. So this material is a self-assembled material, can be directly injected into bone defects and heal bone, as shown in this rabbit study that we conducted many years ago. Similar for cartilage, creating a defect in rabbit cartilage around the knee joint of the rabbit. Here for the non-treatment, we ended up getting fibrocartilage without using a material. Using our material, we end up regenerating cartilage after about 16 weeks. In all of these cases where we've used this material to regenerate tissue, we see little to no inflammation. One thing you remember about COVID-19, it often induces a lot of inflammation. So we were intrigued, again, to use this material to attach to the virus, keep it from replicating, and also reduce inflammation that occurs with COVID-19. So our key question really to ask ourselves around 2019, 2020, when we wanted to contribute to materials that could passivate SARS-CoV-2, is what do we functionalize this molecule with? As I showed you, lysine was the amino acid we used for tissue engineering. We wanted to replace that and use a new peptide that could attach to SARS-CoV-2. The other thing that we wanted to do is we knew from virus research that the spike protein in SARS-CoV-2 was going to mutate. In fact, all of the variants that have occurred since the original Wuhan strain of SARS-CoV-2 involves mutations in the spike protein. So many groups target the spike protein, but we didn't want to because we knew it would mutate. And if it mutates, then the peptide we developed to attach to it is no longer worth its weight. So we targeted another protein called the envelope protein, shown here in this cartoon in the SARS-CoV-2. The envelope protein of these viruses slowly mutates. In fact, only a couple of mutations have been identified in comparison to the numerous mutations that occur in the spike protein. So we used our chemical brains. We came up with, we looked in the literature that showed what is the amino acid sequence of the envelope protein. We developed complementary charged peptides that match the sequence of the envelope protein. We also use molecular dynamics computational software to look at things like Gibbs free energy, van der Waals forces, electrostatic interactions, and chose those peptides that would have a spontaneous attraction to the envelope protein. They would attach quickly and strongly over time to the envelope protein, because if we then took that peptide, and here's two of them that we discovered, take those peptides, attach it to our self-assembled molecule, we now had a way to blanket or passivate the virus. So of course, we wanted to test these in vitro and in vivo. Here's some in vitro results. We use pseudo virus experiments. These can be done in a BL2 lab. In fact, we thought because these could be done in a BL2 lab, we could do this in our university lab, but that was not the case. Again, a reason why I left and started a company in this area. We did these BL2 pseudovirus experiments where the virus can only replicate once. You can measure fluorescence intensity to tell you how much of the virus you have. The x-axis here is the amount of pseudovirus copies. And this particular study was the Wuhan SARS-CoV-2 strain, the original strain of the virus. The different colors on this graph are different concentrations of our molecule, with blue being the control, 0, all the way up, or I should say down, from 1 milligram in orange down to light blue in 1 microgram per ml. And you can see through this experiment, after just 15 minutes, our molecule was able to inhibit roughly 83 to 64% viral replication. Of course, as we all know, what happened is the virus mutated. So we have tested every single mutation that has occurred and received similar results. Here is the latest mutation of SARS-CoV-2, the Omicron variant, which is currently creating problems. Same in vitro experiment, and we were able to see upwards of 90 to 95% inhibition culturing our molecule with the Omicron SARS-CoV-2 variant inhibited about 99%, 95% of viral reproduction. So that was wonderful. We've also seen in our computational modeling and some other experiments that this same molecule, same DNA self-assembled material with peptide can bind to other viruses. It has strong binding to HIV. It has strong binding to influenza, type B and type A. It has strong binding to rhinovirus, the common cold, and other coronaviruses. So we're currently investigating the use of this molecule for a wide range of viruses, not just SARS-CoV-2. Wouldn't it be wonderful if you get a cold that you could go to your local drugstore, get this molecule, have it as a nasal spray, and that would reduce the rhinovirus, something that we have no treatment for in terms of killing that virus. Of course, the proof is in vivo studies and anything you do in biomaterials. So we've done a couple of in vivo translations of this. Our first animal model was a hamster. So we used the Delta SARS-CoV-2 strain. We infected hamsters for up to 4 days. We exposed them through the nose, both for the virus and our molecule. Here are some of the details on this study, the intranasal delivery, different doses we used. We did use the Delta strain in this experiment. We challenged it with a critical dose, and we also used a preventative prophylactic approach where we subjected our molecule to the hamster first and then the virus, or a therapy where we subjected the animal to the virus first and then the molecule, our molecule. So in both of these cases, we were able to identify a dosage, roughly about 0.2 milligrams, that were delivered nasally, intranasally to the hamster, where we saw about a half-log reduction in the RNA for SARS-CoV-2, meaning there was about a half-log reduction of the virus when using our molecule. This was wonderful and great news. Led us to a second experiment, which I'll in the interest of time, describe now. Our second in vivo translation experiment we just finished. We used transgenic mice. So one of the reasons people use the hamster model frequently for SARS-CoV-2 research is hamster cells have the ACE2 receptor, just like we do, in our cells that SARS-CoV-2 attaches to. A mouse does not. So the cells in the lung of a mouse does not have that ACE2 receptor. So in order to use mice in these studies, you have to use transgenic mice. You have to mutate the mouse to have an ACE2 receptor so that the SARS-CoV-2 can attach and then replicate. So again, in this study, we used the Delta strain. This study was just completed by a laboratory in New York State in the United States called the Trudeau Institute. Again, the animal that was used, the administration was intranasal, same as the hamster. We used 3 different doses, higher doses, hoping to get more of a response. We used, again, the Delta strain, a significant challenge of the virus. We had controls which were not subjected to our molecule or any treatment. And we also used Paxlovid. Paxlovid is a drug that is available if you test positive for COVID-19. You can take Paxlovid, and that helps you, supposed to help you get through COVID-19 quicker. However, one of the problems with Paxlovid is once you stop taking the drug, the virus can come back. And that's because Paxlovid acts on an enzyme important for viral replication. It does not encapsulate the virus like our molecule does. So although Paxlovid is FDA approved and is commonly used today, at least in the United States, it does have problems. And it acts via a mechanism that doesn't passivate the virus. It acts on an enzyme that the virus needs for replication. So we used a therapy. We administered these doses every day up to 7 days for a study. Again, here on the y-axis is the amount of RNA from the SARS-CoV-2 Delta strain and the different treatment times down here. This is in the lung. And as you can see on this graph, we were super excited because we're getting 1 log or greater reduction using our higher doses. That's statistically less than the control, and it's statistically the same as an FDA-approved drug, Paxlovid. So we're very excited. We're continuing to look at this molecule and do more studies, but we are seeing equivalent behavior to a currently FDA-approved drug, but it works by a completely different mechanism, by passivating the virus. So therefore, there should be no problems with SARS-CoV-2 coming back, COVID coming back after you stop taking our molecule. Okay, and as we know, the success story for vaccines, Moderna vaccine is one of the more popular vaccines here in the United States. It does use a nanoparticle. So the nanoparticle is a lipid nanoparticle that the mRNA approach that Moderna uses employs. So this is a wonderful success story for nanomedicine. All of the decades of research that have gone into lipid nanoparticles, using them for cancer work, using them for anti-infection work. And here, that work has helped use lipid nanoparticles for a vaccine that is working against COVID COVID-19. So, of course, I could spend the rest of this talk discussing SARS-CoV-2, COVID-19. I do think nanotechnology has already contributed to getting us through COVID-19, and it's helping us get through therapies, develop therapies, preventative, as well as after you're positive, therapies for COVID-19. There are so many other applications of nanomedicine to talk about. And in particular, I also spent my career looking at taking off-the-shelf medical devices and putting nano features on them to improve tissue growth, to decrease infection, to decrease inflammation, all without using drugs. Because remember, as I said in the beginning, I do not think our approach to medicine can be, let's give a patient a drug every time there's a problem, because we have seen that approach does not work. So we take spinal implants, 3D printed spinal implants, put a nanotexture on them to improve bone growth, decrease infection, decrease inflammation. We have also taken spinal screws. Here's an example of a spinal screw in a patient, a human patient, that has been nanotextured through anodization and added some other chemistries to it. And we are seeing significantly improved bone growth as well as zero infection. So this is being commercialized by a company called Nanovi, one of my first spin-out companies, where about 4,500 implants have been inserted into humans today, as of today, with zero cases of infection. And the normal rate for infection for these implants is roughly 5 to 10%, depending on the literature that you see. So changing texture alone, creating this kind of a texture, can decrease bacteria attachment and improve bone cell response without using an antibiotic or a pro-bone growth factor. We've also used this approach for amputees. Here's a rat study that we conducted in which we nanotextured a pin that was put into the remaining limb. And you can see it's just some visual pictures of what that exit wound looks like. 3 days later, the non-nano treated, the current pin that is being used in patients today, the wound was still open. That's that pink region. The wound is still open, prime for bacteria to get in there and infect the implant. In contrast, nanotexturing it, not changing chemistry, just changing roughness, allowed the skin to close, walled off the implant from bacterium, and there were no signs of infection. Stabilization occurred and improved bone growth occurred. And I could go on and on about examples in the vascular community for vascular stents, vascular grafts, in which nanotextures can help re-endothelialization, coverage of that implant by endothelial cells, which is a good thing. Catheters that have nanotextures that can reduce bacteria colonization through those nanotextures alone. Nanotextures that can increase ligament, tendon attachment to metals, which is a big improvement over what is done today, where there is no biological attachment, and even biodegradable metals like magnesium oxide, where you can create nanotextures to decrease degradation of harmful products like hydrogen gas. Of course, I could also spend a great deal of time telling you why, because we've spent 20 years studying why do cells care about nanotextures. Why do they prefer nanotextures to grow tissue? Why do bacteria not like nanotextures? Why do inflammatory cells not like nanotextures? And I can point you to a couple of key findings that we have discovered along the way, and others have discovered along the way. An insect wing has nanotextures, regular arrangement of nanotextures. These nanotextures reduce bacteria growth. So nanotextures are all over the environment, and we're simply borrowing them, using them in our medical devices. I could give you biomechanical, biophysical models, which show that the bacteria membrane is too stiff to attach to all these nano contours. So it doesn't attach, it lifts, and then your immune system clears them. I could give you examples where nanotextures have different energy. Same chemistry, but creating nanotexturing increases surface area, and that changes wettability. And by doing so, you interact with proteins differently on a nanotextured surface compared to micron. Here's fibronectin, a key protein that mammalian cells can attach to. Attaching to a nanotextured surface, it's spread out. It's more bioactive. However, when it attaches to a micron surface, it's more globular, less bioactive. So nanotextures can be used to match the energy of the protein that you want to absorb, and after it absorbs, can change its bioactivity because nanotextures are of the same size as proteins themselves. In fact, I don't have time to get into this, but we've created an equation where you can estimate the width, the length, and the height of nano features to give you the appropriate energy to absorb pro-bone or pro-tissue proteins, or antibacterial proteins, or anti-inflammatory proteins. So in the remaining time that I have, I do want to highlight one important area that's important for us to consider. And that has to do with global warming. And unfortunately, a lot of the work that I've done throughout my career focuses on polymers, metals that leave a big carbon footprint in society. And I think, unfortunately, a lot of my colleagues are in the same situation. We have not embraced environmentally friendly processes in nanotechnology and biomaterial science. In fact, I tend to get the feeling that medical device companies think because they're saving human health, they don't need to care as much about the environment. But I would make a strong argument that some of these same polymers that are polluting our Earth are used in biomaterials: polyvinyl chloride, polyethylene, polystyrene. And whether you think about the implants themselves polluting the environment after they're used, or the polymers we use in our experimental process. One of the biggest polymers used as petri dishes, as 12-well plates for in vitro assays, is polystyrene, which leaves a very large carbon footprint. We all have to do a better job of acknowledging the role that biomaterials are playing in global warming and develop more green approaches. So having said that, I wanted to highlight just one quick example in my lab of where we are developing green nanomedicine. And what I mean by green is either we're using environmentally friendly chemicals to make these nanomaterials, or the materials themselves are environmentally friendly. And one of the things, if you've ever made a nanoparticle, you'll appreciate the toxic chemistries that are used when making nanoparticles. So we wanted to get away from that. We don't want to use these toxic chemicals to make nanoparticles. Instead, we've moved to cells making nanoparticles. You can have bacteria, mammalian cells. If you add the right metal salt, you add them to those cultures and they can make nanoparticles. We've made selenium nanoparticles. We've made iron, silver, gold, platinum. You can make almost any metal on the periodic table. If you get the right starting salt and add it to live cultures, they will produce these materials. So obviously that's wonderful. It reduces our dependency on toxic chemicals that are used during traditional chemical precipitation of nanoparticles. But the other thing is it makes better nanoparticles. So here are some particles made by Staphylococcus aureus. Selenium, nanoparticles made by Staphylococcus aureus. When they're made, they have a protein layer on them. That protein layer reduces cytotoxicity and helps target this particle to killing Staphylococcus aureus over other bacteria. And the reason why that is so important is you have bacteria in your body that you should not kill. E. coli helps you degrade material, degrade food in your stomach. So you don't want to kill all bacteria, you want to be selective. And following this approach, having Staphylococcus aureus make selenium nanoparticles with this protein layer helps these nanoparticles target and selectively kill Staphylococcus aureus. Okay, so here's some raw data showing that. We also have data where MRSA makes selenium nanoparticles, and those particles are more effective at killing MRSA. So let me leave you with just this last slide in the interest of time. and it's our in vivo translation. Of course, we took these same selenium nanoparticles, decorated orthopedic screws, put them in rats for upwards of a week and 4 weeks, and we put bacteria on these implants, so we forced an infection. And when using these selenium nanoparticles, we were able to reduce bacteria growth on the implant, as well as a certain distance away from the implant. So we're able to decrease infection without using an antibiotic and using a very green nano material. So unfortunately, I think I need to stop here. We are doing a lot with implantable sensors that I don't have time to go into. These are intelligent materials that can determine tissue growth in real time around the implant. This is the future, has to be the future of our industry, of our efforts, because sensors have really taken all other fields by storm, except for medical devices. So I hope I gave you a couple of things to think about how nanotechnology is and will be used in the future to fight pandemics, how nanotechnology can decrease our dependency on drugs in our global healthcare system, how nanotechnology can make sensors that are more intelligent, materials that are more intelligent than the inert materials we're implanting today to have personalized medicine. And until we really acknowledge all of these things and develop biomaterials that can accomplish all of these things, we are going to continue to have global healthcare problems that shut down the globe like COVID did. So I thank funding agencies, of course, the companies that are spinning this out, and most definitely my students at the universities I have been at who developed these fundamental studies, which we are now commercializing into real products in humans. Thank you very much, and I'm happy to answer any questions.
It was a pre-recorded presentation, so I don't know if but imagine not Professor Thomas Webster is connected, but imagine no. Professor Sabu, we cannot hear you.
He's not available now. He's on travel, so that's why the video talk. Fantastic.
The talk was about a very hot topic, very interesting, the use of nanotechnology and of tissue engineering materials for COVID treatment. So unfortunately, we cannot ask anything in this moment.
Yeah, because he's in travel. He's traveling quite extensively. Yeah, exactly. Yes. Yeah. So very welcome to you all. Now, what is the next?
Thank you, Dr. Ilaria, for your excellent sharing.
For me, it was a pleasure. Thank you.
And I would also like to thank all the delegates for their interesting presentation in these sections. And now we are going to move on to the next brainstorming section, which will lead by Professor Sabu Thomas, which is Horizon Europe. Horizon Europe is the European Union's new ambitious research and innovation program that runs until 2027, with rolling calls for proposals. So I would like to welcome all the delegates to present a short presentation on your work, and we can have a collaboration with Mahatma Gandhi University and other foreign universities. And I welcome Professor Sabu Thomas to lead this session, and let's have a look on to the session. Please.
Very good afternoon to all my colleagues from Europe, and good morning to all my friends from US, and late good evening to all my friends from Japan and China. Many thanks for the participation in this conference. Dear colleagues, the idea of this session is to have maximum number of cooperative program between participants. So what I'm going to do now is to make a short presentation about Mahatma Gandhi University and our research activities and possible collaborative projects where you can make an application. My university was started in 1983, commemorating the father of our nation, Mahatma Gandhi. A tribute to Mahatma Gandhi for his outstanding work for the nation. You can see my university is located in the southern part of India, called Kerala. You can see from this map. Let me show you some of the achievements of Mahatma Gandhi University. We are NAC. We are #1 with the A grade. We have a 30th position in the country in ARF ranking. According to Times ranking, we are 713 in Times ranking. Times Higher Education ranking, emerging universities 141 rank. Adult ranking, we are in the band of 6 to 25. We have received Chancellor's Award 3 times, 2016, 18, and 19, 20 also we have to add 3 times. India Today ranking, we are pretty good. Our H index of the university is pretty high, highest in the state. You can see our top 200 in the world in the emerging economy university ranking. We are 141. Our university is doing pretty well in terms of publication, in terms of project, in terms of conferences. We are doing it extremely well. You can see our international collaboration. We cooperate with a large number of countries across the globe, in Europe, with the United States, with Africa, with China, with Japan, with Korea, with Taiwan. This is our campus. I am sitting in this campus, the front gate of the university. And this is our website of the university. The campus is extremely green. We have a green campus of 60% coverage. You see our international cooperation network. We cooperate with a large number of institutions across the globe. Chemistry was one of the founding schools of the university. I started my career as a faculty in chemistry. You can see our strength in chemistry departments. We have quite a good number of people in chemistry departments. Chemistry is well equipped. We have all the modern instrumental facilities. This is our new center, International Inter-University Center for Nanoscience, established in 2009. We are a very active nano center. This is my productivity. We are pretty active in terms of publication, in terms of projects, in terms of books. My colleague Nanda Kumar is also pretty active. Young faculty member, Dr. Srikala, she is leading now the Nano Center. We have many grants from different agencies. We have many postdoctoral fellows in the school. These are some of the awards and recognition received by the group. We work with many publishing companies: American Chemical Society, Springer Wiley, Sage, MDPI, Elsevier. We work with all the publishing companies. We offer many programs in the campus in nanoscience and nanotechnology. MS in nanoscience, PhD. We have many funded projects: waste management, energy sector, health sector, sensor manufacturing, food and agriculture, EMI shielders. Look at our infrastructure. We have high-resolution electron microscope, optical microscope, mechanical testing, atomic force microscope. Dear colleagues, we are well equipped. Our facilities are open to all the people within India and abroad. I have a pretty big research team. We have several patents. We are also active in MOOC, massive open online courses. We are very active in water purification filters. You can see we have many exchange programs with many universities abroad. Right now, we have many visitors from abroad. We have many innovative programs. You can see our speakers from abroad, different parts of the world, from Europe, from the United States, from Africa. We also have several Nobel laureates visited us. You can see Professor Ada visited us the last 4 years ago. She was with us. We have many extension activities at the university. We conduct regularly international conferences, at least 4 to 5 international conferences we organize in Nano Center. This is our map towards excellence. You see at 2830, we will come out with a large number of nanotech products. This is our roadmap towards excellence. We are running right now a large number of projects with Israel, with France, with the United States, with Singapore, with the United Kingdom, with Russia. We have a big mega grant running with Russia, the Czech Republic. These are our faculty strength in nanoscience. We offer many courses in energy also. Look at, we have a program on energy materials, energy science. We have MTech in energy science, MSc in nanoscience and nanotechnology. Dear colleagues, I'm now going to present you EU India program, Horizon Europe. Horizon Europe provides us lots of opportunity to collaborate. So I request all my colleagues to look at the European calls. Some of the calls are India specific. There are a lot of opportunities for us to work together. Basically, a sustainable, fair, prosperous future of people. That is the main motto of Horizon Europe. You can see the Horizon Europe's funding possibilities. Quite a good amount of funding for R&D investment. I have mentioned the vision of Horizon Europe, climate change, sustainable development goals. Basically, European Union, the Horizon Europe boosts EU's competitiveness and growth process, create jobs. Let me now show you how we can apply for the European program. What is Horizon Europe? Horizon Europe is the research and innovation framework running from 2021-27. So we have 22, now is running 22, 23. So there are many years to go. So I request everyone to look into the website of Horizon Europe and look at all the calls. Then we will be able to apply for a specific call. And calls are actually on a variety of fields: climate change, cancer health, healthy oceans, environmental remediation, soil remediation, food security issues. How to apply for funding? You know, the way of funding for European program is, I request all my colleagues to look at the calls on a daily basis. And once you see the call, you network and collaborate with a large number of people in Europe, including some industries. Then formulate a challenging proposal, submit online to European Union. And partnership is very important. You know, you have to really find large number of partners. Even European Union website also will help you to find partners. And evaluation is quite strict, very rigorous evaluation. Each project is reviewed in Brussels. Once you have the grant, you know, then it's very easy, very good. But dear colleagues, the success rate is less than 20%. And we have to work to submit a proposal. You have to work at least 6 months. You have to work extremely hard to submit a proposal. So these are some of the web details of European Union. I request everyone to register on the European Union website. Then you get calls on a regular basis. I will send you this presentation to all my colleagues. Now I'm going to tell you there are lots of other possibilities. Postdoctoral fellowship under European Union, Marie Curie fellowships, Action Fellowship. You can see the deadline is 14 September. This is a very interesting fellowship. European Research Council Work Program 2021 and 2022. Let me now show you some of the national calls for my Indian colleagues. Within India, you can apply for a large number of projects within India. So I've listed all the important funding agencies within the country. Look at the international agencies. American Academy of Rome, Association of Commonwealth Universities, British Council, British Institute of Eastern Africa. There are a lot of funding agencies within the country. Toyota Foundation, ASEAN Project, UNESCO, UNDP. These are all multilateral programs. Dear colleagues, additionally, I also want to tell you that Government of India has signed agreement with a large number of countries. I have ordered in the alphabetical fashion: Argentina, Armenia, Austria. You can see. At the end is Zambia. So you can see large number of countries with whom Government of India has signed MOUs, and we can work with all these countries. Every year you have lots of calls are coming. And my group was lucky enough to get a large number of grants under this. Indo-French is a very interesting program. We are running an Indo-French program now under CEFIPRA. CEFIPRA, you can apply twice in a year. National Science Foundation, we can apply twice in a year, 1st September and 1st February. Indo-US Science Technology Forum program, Indo-German program. Dear colleagues, now I'm going to show you some of the ongoing calls. ASEAN call is open now. India-Belarus program is open now. DST Accelerating CC US program is open now. India-Japan is open now. We have a Japanese colleague, but he is located in Taiwan, but we can request him. India-Canada is open now. I am applying for the India-Canada program now. India-Swedish program, the last date is June 15, India-Swedish program. There's a joint call proposal, circular economy. June 15, and it's I think it's ending in August 17. SADI proposal of Government of India. There's another call for advanced materials for energy storage technology. There's a very interesting call that is within India. Women Scientist Scheme of Government of India is very interesting for our lady faculty members, lady members. SCRB Power is a very interesting program exclusively for women. SCRB Power program. There is ICMR DFG call proposal. 30th September is the last date. Basically for occupational regulatory and systemic toxicology studies. Agri-Tech program. Fulbright Nehru Academic and Professional Excellence program with the US. So these are some of the calls. So there are many, many calls. I request my colleagues and friends to apply for all these programs. Now, very briefly, I will show you my research activities. Dear colleagues, my group is very active in multi-phase polymer systems, particularly on polymer blends. We develop different types of morphological structures. You can see beautiful morphological structures we develop. These are all different morphologies we developed, and these morphologies could be monitored by electron microscopy, spectroscopy, atomic force microscopy. All these techniques could be utilized. Next movie, the movie. Slow. Yeah, this is some of the nanostructures blends we have developed. My group is able to develop micro nanostructure systems. Yeah, we are able to make corsal structures, worm-like structures. These are some of the structures we have developed. We are also into developing membranes for nanocomposite. You can see we have developed some nice membranes for tire engineering. Pure natural rubber, the permeability is so high, but when you put bentonite or photohexoride, you can see the permeability has been decreased dramatically. We are into nanocellulose. You can see nanocellulose is very important activity in our group. Nanocellulose for medical applications, engineering applications, for sensors. We are into biomedical applications. You can see scaffold. Nanocellulose for scaffold. Nanocellulose for water purification. We are also into interpenetrating polymer network systems. We work on recycling. We work on recycling quite a lot. ഈ കമ്പ്യൂട്ടർ ഇഷ്യൂ ആയിരിക്കും അല്ലേ?
എന്റെ ആണോ അറിയത്തില്ല, അതിന്റെ ആയിരിക്കും.
Okay. Yeah, I will finish soon. Not much of. Oh, internet issue?
Yes.
Yeah. Okay now. Maybe it's okay. Okay. It's slowly. Yeah, we will load in the screen in the other computer, so probably we can see it at a faster rate. Dear colleagues, we develop a large number of multi-phase systems. It could be super tough epoxies. It could be interpenetrating networks. You leave that. This is enough.
I'll close the
Close it. There is some problem with the computer, so yes.
MGU IIUCNN करती हूँ. Presentation.
Yeah.
Slow.
Okay.
Slow.
Yeah, a bit slow. Dear colleagues, we also work with many tire companies. basically to make impermeable membranes. You can see these are some of the tire companies we work, Apollo Tires, MRF Tires. We are also working on electrically conducting systems for EMI shielding. This is also one of our important activity. EMI shield is for electronic instruments. You can see some of the systems we have developed for EMI shielding applications. We are into multi-volt carbon nanotube, putting into natural rubber and synthetic rubbers. You can see we made EMI shielders using SBR and carbon nanotube. Now I will show you some of the work we have done with the General Cable United States. We had a big program with the General Cable United States. What we did is we introduced hybrid structures, hybrid fillets, different types of nano fillets into a polymeric matrix. And you can see self-assembly process. We've got a beautiful self-assembly, where we developed impermeable cable compound with the cable company. Dear colleagues, we are also into making sensors, pressure sensors. Today we all listen to the nice talk of our Italian colleague working on a sensor. So we made a variety of strain sensors using elastomers. We are also into green tires. Dear colleagues, the tire is black because of the carbon black. So we are trying to make a silica-filled tires. So this is again a very important program, hybrid nanofillers in green tires. We are into epoxies in a big way to make epoxy super tough by making nanostructures. Cooperation with my German colleague, Professor Jürgen Piontek in Dresden. So we have many students working in this area. We also into viscoelastic phase suppression process, again with a Polish collaborator, Professor Wingler. Look at our sensor work, pressure sensors with flexible rubbers. We are also into thin films. This is again a very cooperative program with France. We have a very active program with France on thin films. Dear colleagues, we are into biomedical applications. We all must have listened to the talk of Thomas Webster now from the United States. So we do electrospinning and make advanced material for tissue engineering, wound healing applications. We also do 3D printed scaffold for tissue regeneration process. We are also into nanocellulose in a big way, cooperating with the Brazil, United States, Canada, and France, and Sweden. We make variety of nanostructures. We do water purification membranes. We do, edible coating for fruits to preserve fruits and vegetables. You can see biopolymers for edible coating. This is a big area in our group. Dear colleagues, we are also funded heavily by a large number of agencies within India and abroad. For a good amount of funding we received. We can see our collaborators worldwide. Companies. You can see our research profile with my colleagues from abroad. We are also into the other number of books, editing and writing books. More than now 170 books now, our group. You can see our group members in chemistry, nanoscience, and energy science. Dear colleagues, I'm also an editor of nanostructures and nano objects. We are waiting for the impact factor. The site score is 10 now. So those who work on nano, please submit your articles. Some nice pictures of Kerala. We have 2 conferences coming up. International Online Conference on Recycling. International Online Conference on Membrane. We are also going to have a conference on outcome-based education, probably next year. So thank you so much. Let me quote our father of our nation: true education is that which proves usefulness in life and make you industrious. So dear colleagues, my university is open to all sorts of collaboration. We can work together. We can submit joint proposals. And I am looking forward to have you in our campus probably next year after COVID. Thank you so much. And we are looking forward to listen to you. Each of you can present 1 or 2 slides. And if you have any questions, you can ask me. Thank you.
So can I share some of?
Yes, please, please. Please share your slide. Yeah, thank you.
Thank you very much.
Yeah, thank you.
So actually, I have not prepared full slides. So I would like to share my current work first.
Yeah.
So this is my profile. I did my PhD in Chubu University. I was Mombusho Fellow over there. I did my doctoral study on Fe3O4 nanoparticle synthesis and their applications in cancer hypothermia. Right now.
Hello, excuse me. Hello,
Yes,
Ajay sir. We are not able to see your presentation. Could you please share it again?
Yeah. Yeah, can you see now?
No, sir. It is loading. Yes. Can you make it full screen? Yes.
Yeah.
Enough.
Quickly, 1 or 2. Yeah.
So this is my profile. As I mentioned, I did my doctoral study in Chubu University. I was Mombusho Fellow over there. My PhD thesis was on Fe3O4 nanoparticle synthesis and their applications in cancer hyperthermia. So right now I'm working as a postdoc at King's Mongkut University Sensor Technology Laboratory. Right now I'm working on creatinine detection by using bimetallic nanoparticles. I'm also associated with Nano Theranostics, which is in New York, and we are working on advanced nano materials there. I'm also associated with SIIT, that is Shenzhen Institute of Advanced Technology, Chinese Academy of Sciences. My postdoc position was paused due to COVID, so I got like overseas contract. So this is like my recent work. So recently we submitted one manuscript to Nature Materials, and I published one article on silver nanoparticles in nanoscale, and the other one based on black phosphorus. So I would like to collaborate in some project. I would like to write any proposal suitable to my research area. Thank you very much for listening me. Yeah, thank you very much for your time.
Okay.
Thank
you, Ajay.
Thank you, Ajinkya, for the presentation, and you have done a good work. And next, I would like to welcome Professor Christopher. Professor Christopher, are you here? Professor Blessing.
What are they saying now?
Professor Blessing, do you have something to share with us?
I did not prepare any slide to share with you, but I'll just tell you a little bit of what I'm currently involved in.
Yes,
I'm currently involved in the design of wound dressing, polymer-based wound dressing. I'm also into design of polymer-based drug delivery systems. And what we are looking at currently are the polymer drug conjugates. And I'm also into organic synthesis. We are into the synthesis of hybrid molecules with anti-cancer, anti-malaria, and antibacterial activity.
Okay, Dr. Shabnam Khan, could you please share your proposal?
Yeah, thank you so much.
We cannot hear you very clearly.
Okay. Can you now hear me? Am I
Yes.
audible?
Yes.
Okay. So thank you. Good evening, everyone. Thank you for this opportunity, Professor Thomas, and the organizers of the conference. Now I would like to present a small proposal that I have in mind that I think yeah. I hope my presentation is visible.
Yes.
Okay. So the project proposal for Horizon Europe ICN 2022. I'm Dr. Shabnam Khan from Department of Chemistry, Sam Higginbotham University of Agriculture, Technology and Sciences, Allahabad, India. So my proposal is for the development of nano-engineered scaffolds for smart wound dressing and other therapeutic applications. It is proposed to develop a smart wound dressing using silver and copper nanoparticle with some medicinal plants, leaves, and flower extract. The synthesized nanoparticle will be incorporated with the magnetic nanoparticles and will then be impregnated on a bandage. This nano mesh will be tested on a cuticular wound. Similarly, the green synthesized nanoparticle will be explored for antifungal, antibacterial, and anti-inflammatory activities. In order to develop the smart dressing, the magnetic material needs to be grafted onto the wound dressing material. Most wound dressing materials have cellulose, whose main purpose is to absorb excess moisture, which represents an attractive target for grafting. A prospective and promising option is tackling this challenge, which is like in a normal dressing, what we do, we dress it and we undress it after some time. So it also requires materials. So I just want to develop a dressing that will self-heal along with the incorporation of magnetic nanoparticle that will in which temperature will act as a biomarker. So the MNP will be used as wound healing monitoring system using temperature as a biomarker capable of wireless communication. The system will use the ability of nanomaterial with varying magnetic properties to respond to temperature changes. In this future work, the ferromagnetic nanoparticle will be synthesized and used due to their capability to produce temperature dependent magnetic properties. So this is a schematic of what I just want to do, like preparing green nanoparticles and then incorporating with a magnetic nanoparticle, in which temperature will act as a biomarker, then impregnate it on a bandage, and then it will be used for wound healing. So thank you so much. This was a small idea that I wanted to share with you all. Thank you.
Thank you, Dr. Shabnam Khan. Do you is there are any questions? Are there any questions to share from the audience? Are there any questions to share with Dr. Shabnam?
Sir, I have something to discuss with Dr. Shabnam. Can I?
Yes, ma'am.
Yeah, this is Iffa Zareen Ahmed. I am professor at Integral University, Lucknow.
Yeah.
Very nice idea, Dr. Shabnam.
Yes.
Actually, our lab is also working in this area of wound healing patches.
Yeah, ma'am.
So what I am proposing, sir, I am Dr. Sabu. I am applying for the big ignition grant of BIRAC. You must be aware of that. They are funding some ideas which could be commercialized. So I am proposing a wound healing patch which contains the cytonemin, which is a pigment which is found in some cyanobacterial strain. It shows UV protective activity. So I'm proposing, and we have done almost 50% of the work also in this area. So we are proposing a wound healing patch which will contain cytonemin as a UV protective pigment, and it also shows some wound healing activities. It is supplemented with Cydonia oblonga, golden apple seed extract. Cydonia oblonga extract is well known for its wound healing properties. So these two bioactive components will be there on the wound healing patch, and we are proposing to have some biosensor which would tell from time to time whether the wound has been healed or not. So it is an idea which we would like to submit in big ignition grant of BIRAC. So if you would, if you are interested in collaborating with us, Dr. Shabnam, I would be happy to do so.
Definitely, I would like to collaborate with you.
Thank you so much, sir.
Yes, that was so nice to have a collaboration between the two groups. So, are there any further comments or suggestions? If so, I would like to move to Professor Kash Gandhi. Can you please share some of your works and few words?
Yes, I will share my screen. Hi, Sabu. Hi, Professor Thomas, and everyone. That was a great first day conference, and I like your idea of these discussions for collaboration. So let me share my screen first. So can you please tell me if you can see my screen?
Yes.
Okay, so I'm going to put it as so you can see it and you can hear me well, right?
Yes. Yes.
Okay, great. So our research is multifaceted. A part of our maybe the core of our research is physical, theoretical, and computational chemistry, but with applications to materials. So what we do, we try to synthesize, for example, green materials for different applications, but from a very microscopic point of view, looking at physical and computational aspects, and that would be the feed for our applications. The focus is on green free radical polymerization and radiation chemistry in particular, with applications to green free radical polymerization methods, radiation therapy, better nuclear reactors, which is in the category of energy, or looking into the decay of material in energy applications. For example, how material in solar cells would get damaged, how the batteries get damaged, and try to find out the mechanism so that we can prevent the damage. that type of research are within the realm of the green chemistry. So after we do the physical chemistry studies to understand the mechanism, we come up with green methods for synthesis for both materials and inorganic, organic, and composite inorganic, organic materials. Some of our work on materials are on magnetic and electrical properties of materials and nanomaterials, and in particular, we put microscopic probes inside the material. So imagine that you have a magnetometer within a nanometer scale that you can put it in different places in nanomaterial. So we have access to such techniques, and therefore we can get properties both locally at a microscopic level and globally at the macroscopic level, both for the magnetic and electrical properties. One of the work that we have been doing over the last 20 years is moving away from chemicals as much as possible and moving towards using external fields as a mode of green chemistry for synthesis and applications of materials. And that led to new medical devices and new therapeutic applications as well, because whatever we can do in chemical synthesis, we can do it in the body too, to attack pathogens, for example, or cancer cells. And because lots of these works involve making instruments, we got very good in developing new instrumentations, new spectroscopic instruments, and new sensors to probe mechanisms of interactions of, for example, material with biological material. And another aspect of our techniques is non-destructive chemical analysis under the surface. As far as I can say, I think that's the only technique that exists, that it can go from all the way from sub-nanometer all the way to centimeter, depending on the material, under the surface, and we can probe what is happening under the surface in a non-destructive manner without any damage to the material. Because of this, we got into environmental waste management, and of course these are all have applications in nuclear electricity and heat. Anything that would have applications in radiation therapy would have also applications in nuclear electricity and heat. So first I want to thank Professor Thomas and all colleagues for organizing this, but also I wanted to tell a little bit about our graduate program. So our graduate program is Guelph Waterloo graduate program. So this is one of the largest graduate programs in chemistry in Canada. It's either the first or the second. It's competing always with University of Toronto. We have 64 faculty in chemistry, and therefore we can apply, offer many graduate courses and a wide variety of research fields within the university. But also I'm very much connected to collaborators. I have collaborated with Professor Thomas before. I would enjoy more collaboration. I have collaborations with Japan, England, France, and Switzerland. So I would be happy to collaborate on projects both within Canada, India, and Canada, India, Europe. Thanks.
Thank you, Dr. Kashgandhi sir, for your presentation and introduction of your group.
There's a recent call. We should apply for that.
Yes, yes. I got your email. We should work on that. Yes, that's great.
Thank you. Yeah.
Thank you.
Yeah.
Yeah, thank you so much, sir, for introducing your group and research activity. And is there any questions from the audience to have discussed with Kashgandhi, sir? Please. So I welcome Dr. T. Murugadas, sir, to discuss his presentation on his work. So.
Yes, thank you, Professor, for the opportunity, and I'm really happy to have a huge crowd of researchers from everywhere. So I have prepared just a few slides using my recent publications. Sorry. So we are working on thin film field effect transistors and electronic biosensors. As I said earlier, we have a platform which is carbon nanotube field effect transistors. So if anybody have a receptor which is sensitive to a target or a poisonous molecule, then we can immobilize the receptor into the carbon nanotube field effect transistors, and we can make it as a sensor. So we have no big crowd, no big people here in Sri Lanka to fabricate biomolecules for us. So if anybody interested in biosensors, making selective biosensors, sorry. So we were successfully demonstrated a coronavirus detecting biosensor, but because of the lack of facilities in our universities, we couldn't make a real sensor with real viral samples. So we did a proof of concept work and we published it. And also we have published 2 different works using carbon nanotube field effect transistors. Also, I am really interested on field effect transistors, not only for biosensing applications. It could be either a polymer material or a metal oxide thin film or a chalcogenide or anything, any thin film material. We can make it as a field effect transistors, which people are looking for, even integrated circuit applications. And if it is an optically sensitive material, we can make it as an OFET or optically gateable field effect transistors. So what here we have is I have developed a nice facility to fabricate the field effect transistors and test them. But variety of materials can come from a variety of groups, especially semiconducting polymers or semiconducting thin film materials. So we can make them into field effect transistors and we can test them, we can study them electronically. Or even at the next step, we can make them into field effect transistor based biosensors to detect several biomolecules with the help of biologists. So these are the 2 key fields which I would like to involve in any group everywhere from Sri Lanka. So that's all my work, and thank you from Sri Lanka. Thank you for all the love. Thank you.
Thank you, Dr. T. Murugadas, sir, for your presentation. So next, I would like to welcome Dr. Ilaria, ma'am, for her presentation and introduction of her group and research activities. Please. Dr. Ilaria, are you there? Dr. Ilaria? Let's hold for 1 minute, please. Ilaria ma'am is sharing her PPT soon. So till that time, anyone have any questions? You can discuss each other. So those who have raised their hands also can have a discussion.
Yes, very good evening to everyone. I would like to thank Professor Sabudama sir for organizing this wonderful interaction session. And sir mentioned, Murugadas sir mentioned about his research activities. I would like to discuss something related to the biosensors. And shall I start presenting my screen? for a while. So what is the work which we are doing? Since the work whichever you have said, which is we are developing a series of sensors, especially on electrochemical biosensor and photoluminescence based biosensor, and of course for a chemical gas sensor. Shall I share my PPT for a while? Hello, am I audible?
Yes, you are audible.
Yeah, shall I share the PPT in a while?
Yes, you can.
Yeah, yes. So whether my screen is visible?
Yes, can you please make it? Yes.
Yes. Basically we are working on nanostructure based sensors for food quality, environmental and healthcare application. During my invited talk in the morning, I have projected these slides also there, but here for this discussion again, let me show whatever the work which we are doing on. And yes, so this is what actually we are working on, different nanostructure based sensors for healthcare application. Especially we'll be developing sensors for monitoring the exhaled breath. So we'll be analyzing the exhaled breath and we'll be able to correlate to the specific diseases. So this is on thin film based, different nanostructure based sensors we are fabricating on that particular application. And as far as the healthcare application is concerned, we are also working on developing photoluminescence based biosensor for the early detection of urinary tract infections using quorum sensing signals. So that is also a particular work which we are working on, photoluminescence based sensors and food quality application. So we are developing again a series of sensors using metal oxide based nanostructure, and now we are exploring 2D materials also in that particular case, and environmental monitoring application also. So we will be developing a chemoresistive type of sensors, especially as Mundada sir said, we'll be working on field effect transistor based electronic sensors. So we are also working on that, but closely related to chemoresistive based sensors for environmental application. So in the next 2 to 3 slides, let me summarize whatever the activities which we are doing. As far as the healthcare application is concerned, as I said, we are developing a sensors for finding out urinary tract infection at the earliest stages using a titanium oxide nanoparticle and zinc oxide nanoparticle by sensing the quorum sensing signal, that is acyl rhomosol and lactose. So this is actually one work which we are working on, electrochemical, that is photoluminescence based biosensor. And as far as the chemoresistive type sensor is concerned, we are working on developing different heterostructured based sensor, ZN1 CDO heterostructure as well as heterojunction based sensor, and we'll be investigating more on surface activating the material with UV and optical source. And we are developing a series of breath sensors for also for that particular case. So this is a work which we are working on. No, I'm just highlighting a few important work over here. We have done a series of sensors there for the healthcare applications, and similarly we are working on developing these sensors for food quality. So here, from the material to device fabrication, that is what we are working on, developing a sensors for for identifying the quality of the seafood sample. So this is one particular case where we have developed this prototype, especially starting from the material. We have developed a sensor and we have made it as a prototype, and we have integrated the IoT as well as all the circuitry part, and we made a device. So this is what actually we're working on, the food quality analysis. And on the right hand side, I have shown this is for identifying the formalin levels in fishes. Nowadays we used to have the formalin for preservative, right? So in general, the fishermen, they would not follow the same standard that is allowed threshold limit. So the sensor which we have developed is based on electrochemical based sensor. It is for detection of formalin. So it is showing a comparator effect. So this is a recent published in 2020. So this is also on the food quality analysis. So coming to the environmental application, we are working on again a detection of larger number of species, especially larger number of air pollutants through the resistor type of sensing, where we have explored different nanostructures of metal oxide as a thin film or a nanoparticles or even sensitized nanoparticles. So all these things will come into the category of environmental application where we are working on. And the second thing is we are also working on detecting heavy metal ions as well as chemical residues in the water bodies using electrochemical based biosensor again. So these are the recent works which have been published in this particular area. And also we started working on developing the sensors on using 2D materials, especially carbon nitride material and microporous polymers, that is POPs, porous organic polymers. So these are all the investigation which we are making, especially for healthcare, environmental, and biosensing application. So these are all the recent publications of it. So where we are working on with the different materials. So thank you once again for the opportunity, and I'll be really interesting to work with the very young people here. Yeah, thank you so much.
Thank you, Srinivasan sir, for your presentation. So next I would like to welcome Dr. Ilaria ma'am for her presentation.
Yes, thank you. Sorry. So really, I have a generic presentation about the activity of my groups, but of course I will be very short. It can be very briefly, just only to introduce our activity. I'm Ilaria Cacciotti. I'm full professor in material science and technology and biomaterials and tissue engineering. So our activities are about the formulation, the development, the production, characterization of advanced biomaterials for application in several sectors, just not only the biomedical, even if we are talking about biomaterials, but also in the environmental and the food sector. Just only to show you our laboratories, we have chemical laboratories completely equipped with everything necessary in order to produce materials lab with the processing instruments such as different kind of additive manufacturing machine, fuse deposition modeling, but also stereolithography, digital light processing, and also a setup for electrospinning for the production of fibers, instrumentation for the production of coatings, for example, deep coater, but also aerography. And for the characterization, we have the differential scanning calorimetry, the polarized optical microscope, different instrumentation for the mechanical test, both for dynamical mechanical test, but also for the statical one, and also a mechanical lab for the preparation of materials with a CNC, for example, a measurement lab for different electrical and mechanical measurements. And also we have free direct access to X-ray diffraction, infrared spectroscopy, scanning electron microscope. In particular, in this moment, we are acquiring different new instrumentation, an infrared spectroscopy, mini spray dryer, high performance liquid chromatography, selective laser sintering for polymers, a viscosimeter, and so on. Regarding our activities, just only to show you my group. My group is composed, as you can see, of different expertise, electronic engineering, but also chemical ones, material science, chemistry, industrial chemistry, biomedical engineer, and so on. Just only to show you that we need, for an interdisciplinary approach, a multidisciplinary staff. So the main topic, as I told you before, our activities is focused on the formulation, production, processing, characterization of biomaterials for biomedical applications, but also for application in the food sector and in the environmental sector. For example, for the environmental sector, we were involved in a European project for the production of anti-fouling coatings based on biopolymeric materials as an alternative to the commonly used paints based on biocide materials in order to overcome environmental problems. Moreover, we are also involved in production in particles, films, fibers for water purification using also in this case biomaterials, in particular polysaccharides. and in the production in another European project of eco-sustainable protective and photocatalytic coatings for applications in civil engineering, in the cultural heritage and so on, using biocompatible materials, for example, titanium dioxide and hydroxyapatite. Moreover, okay, as I told you before, we are also involved in application regarding the food sector, in particular the production of materials for food packaging by solvent casting approach, but also by electrospinning. So we are involved in the production of compostable materials using compostable polymers. In order to overcome their limits, we are involved in the production of composite materials with the addition of specific fillers in order to increase mechanical properties, to enhance the gas barrier properties, to provide antibacterial, antioxidant functionalities, and so on. In particular, we are working on the reuse of agri-food waste materials, agri-food waste fillers, characterized by high availability and low cost, in order to propose eco-sustainable alternatives for a smart and sustainable waste management in agreement with the circular economy approach and with the zero waste standard vision. For example, we are using calcium carbonate from eggshell, seashell, mollusk shell, clam shell, and so on, and also the atomite. And to provide antimicrobial, antioxidant properties, we are using extract from fruit waste, from coffee ground, from licorice, from garlic, and so on. I'll show you some results tomorrow in my plenary speech.
Hello, excuse me, Dr. Ilaria.
I'm going to the conclusion.
Yes.
So,
Yeah.
for example, also we are also producing biocatalysts for a bioreactor for the clarification of a beverage, and also application in biomedical sector, for example, in tissue engineering, with the production of nanoparticles and of coating, scaffold, composite. But I'll show you something about this tomorrow. So just only to let you know our activities. Also the use, for example, additive manufacturing in the biomedical sector for the production of implants. So just only a very, very brief introduction about our activities. If you have any questions, and of course we are available for submitting a common project about these topics.
Oh, thank you so much, Dr. Ilaria, for a wonderful presentation. And we have a limited sort of time. That's why we have about to conclude. And if anyone have any question, like Professor Vedahari sir want to discuss something, so please conclude in a short time.
One slide.
Yes, one slide you can.
Sir, before that, can I ask something to Ms. Ilaria?
Yes, please.
Hi, I'm Bindu Krishnan. I'm currently trying to develop. Actually, we have just succeeded in developing carbon dots from natural Ayurvedic medicinal plants. So, is there any way you would like to incorporate that in polymer metrics and use for some applications? Because you said you want to try new nano fillers in the polymer.
Yeah. So of course, for example, they would be very interesting, innovative nano fillers to improve, for example, some specific functionalities, mechanical properties, or other ones. Also to provide, since they are from natural source.
Natural materials, carbon dots we are developing. Carbon dots from natural materials like Ayurvedic medicinal plants. So
I imagine that probably they could have also, for example, antimicrobial, antioxidant properties.
Yes.
So
they have.
I imagine. So for this reason, they could be very interesting to incorporate within our materials. Probably we can share our email address and to contact each other. I can write here my email address.
Thank you.
Okay, thank you, ma'am. So, Dr. Professor Vedahari sir, you can present a single slide, and that can concise your work, and please present in a concise manner. We have limited amount of time, that's why.
Yeah.
Yeah, thank you so much. I just share my PowerPoint so that is it visible?
No, sir, it is not visible yet. Yes, it is loading.
Yeah. Okay, my video is off. No problem. Myself, Dr. Vedahari. Now I am working as Olam Nava Fellow, sponsored by NAVA, Government of Poland. So now I am working developing long-acting injectable for HIV. So here we are using different polymers like PLA and chitosan, developing by spray drying technique as well as microfluidic techniques. So later we'll be converting these nanoparticle loaded into oleogel. Is a like a new technique, a new kind of a gel. It's being used mostly in the food industry. Now we are proposing for long-acting injectable. So recently one of our paper accepted a revision in one of the good journal. So like chitosan loaded nanoparticles. So this is one of the main area that I am working now. I am interested in collaboration, like any of you interested, and we are also working with the different nanoparticles, and this is catheter coated with the chitosan for the first time, isolated from new source, also like as a DBT funded project in India. And we also synthesize aluminum oxide nanoparticles for various applications. So this is one we used for mechanical. Also, we are working for vaccines, etc. And also, I'm working on 3D printing technology. We optimized a gel like for 3D printing, and it is working well. So these are the different shapes that we produced. So that's all. Thank you for the opportunity, Professor Sabu Thomas and the team. So thank you.
Sir, can I just project one slide to show Miss Ilaria and if anybody else about the carbon dot fluorescence that I got?
Yes, you can present in a one
only
slide.
2 slides. Yeah.
Yes, please. In a short time.
Yeah, just 2 slides. Hope this is visible.
No, it's not visible yet. It's not visible yet. Could you please share again?
Yeah.
Dr. Shaini, are you sharing the PPT?
Yeah, I'm trying to share. Sir,
Yes, sir, I'm ready.
No, this is not.
Sir. Hello. Sir, am I audible?
Yes, you are audible. Are you sharing the PPT?
Yeah. Sir, just 2 slides I have to share.
Okay, please.
ഇതിലേക്ക് വരാൻ എന്താ ചെയ്യാ ഇത് ക്ലിക്ക് ചെയ്യും അത് ക്ലിക്ക് ചെയ്താൽ ഇത് തന്നെ വരണേ എന്റെ പവർ പോയിന്റ് വരണില്ല
Yes, please carry on, Shaini ma'am. Your PPT is visible now. Hello, Shiny ma'am, are you there?
Sir?
You are audible. Please carry on.
Okay, thank you. So good evening all, and I'm Shiny, working as assistant professor in the Department of Physics of Government Arts and Science College, Calicut. And here is my project proposal under Horizon Europe. And title of the proposal is Synthesis, Characterization, Property Studies, and Device Fabrication of Thermoelectric Materials Suitable for Waste Heat Recovery. Basically, I'm working in the field of thermoelectricity, and these thermoelectric materials are capable of interconverting heat and electrical energy. And here are the broad objectives of the present proposal. Firstly, we need to develop inorganic N and P-type thermoelectric materials with a better conversion efficiency. And we are particularly interested in chalcogenide materials and oxide materials for near room temperature applications and high temperature applications. And we need to explore the impact of inculcating nanostructures, including graphite carbon nitride, then graphene and carbon quantum dots on the thermoelectric performance of already established thermoelectric materials like bismuth telluride based composites. And definitely for tuning the properties or electrical and thermal transport properties of these nanocomposites, we need theoretical investigations based on first principle studies and atomistic simulations. And we have just started this particular area. We are beginners in this area, and we are now working with Gaussian software. And I welcome a person with expertise in these softwares like Materials Studio and Quantum Espresso, like that, for theoretical investigations in tuning or in designing new nanocomposites, inorganic thermoelectric nanocomposites. Then again, we need to design and develop polymer nanocomposite thermoelectric materials. It's a new fast developing area, and we are interested in tuning the electrical properties of polymer nanocomposites and to make them suitable for thermoelectric conversion. And we need collaboration in this area also to tune the properties of materials like PEDOT, polyaniline, fanning, like that, by including graphite carbon nitride like materials. And finally, we need thermoelectric device fabrication. We need to design the thermoelectric generators and to measure their properties. And here in this area also, I welcome collaboration from electrical engineering people. And so these are the possible areas of collaboration, and it is the motivation and our previous research experience. I'm already collaborated with the University of Calicut, and there we have facility to measure this thermoelectric properties and for some synthesis part. And these are some of our recent publications. Once again, I invite the collaborations in these areas. So thank you.
Okay, thank you, Dr. Shiny, for your presentation. So I hope let's wind up this session for today.
Sir, if you give me 2 minutes, I would like to share my slides, sir. Just 2 minutes if you have.
One slide. So please share in a one slide because we have a limited short of time. We want to conclude.
Excuse me, sir, I have got. Sir, I've been trying to share earlier about the carbon dots to Miss Elena. Can I do that?
Is my slide visible to all of you?
Yes, it is visible.
Okay, sir. This is my area of research. I am developing the nano emulsion incorporated cosmeceutical products. The nano emulsion is based on the pigment cytonemin, which is UV protective compound present in cyanobacteria, Cytonema javanicum. So I have prepared the nano emulsion of this pigment and incorporated it into the cosmeceutical products. I will just show. We have worked on the skin cancer cell line, that is HICAT. These are keratinocytes. We have characterized the nano emulsion, which is based on the cytonemin pigment. Then we have analyzed it using the HICAT, that is skin cancer cell lines, under in vitro conditions, and it is giving very promising results under with the skin cancer cells. These are some of the results which I am showing here. Then what I've done, I've incorporated this nano emulsion into cosmeceutical products. Two types of cosmeceutical products I have developed, that is the nano emulsion based gel and the nano emulsion based cream. We have also asking for the patent for these products. So these nano emulsion based cosmeceutical products are very stable. We have tested the stability and they are showing antimicrobial properties also. The pH value, the odor, color, texture, physical appearance is all up to the mark. We have also done its in vivo evaluation on the rat skins. It is showing very promising results. The next project which I've worked in, it is funded by the Ministry of IUCNN, in which I have worked on the Nigella sativa sprouts to see its anti-cancer activities on the liver cell lines, liver cancers. And it also has given me very good results, very good outputs. The anti-cancer activity of the nano-structured lipid carriers, which is based on the bioactive compounds thymol and thymoquinone of Nigella sativa, which is a popular spice used in every household. I've prepared the sprout of this spice, and then I've incorporated and I've prepared the nano-structured lipid carriers, and have seen this activity on the liver cancer cell line, and it has given me very promising results. So if anybody is interested to collaborate with me in these areas, I would be happy to do so. Thank you so much, sir, for giving me time and the opportunity to present my work here.
Yes.
Thank you so much.
Thank you,
Excuse me, sir. I've got only one slide. If you don't mind, can I go ahead? This is Anjana.
Please. Yes, please. Present in a short time, please.
Yeah, thank you. Yes, good evening all. Once again, I thank Professor Sabu Thomas and the organizers for giving me the opportunity. As such, I'm not a big person and I do not have a big group, but this is what I have done so far. I could rather done so far. I have completed 3 of my projects. 2 are funded with DST, 1 with CSIR with around 55 lakhs total grant mobilization. And basically, I have been working, as I am residing at a coastal city, I have been working on marine-derived fungi. I have explored various dimensions of this, like bioremediation, then enzyme production, as well as I have rather worked on biosynthesis of nanoparticles and their applications in photonics, as well as biomedical applications. So I was under impression that just as I am a visiting faculty, I cannot collaborate, but while having a email conversation with Professor Thomas, I could know that even being a visiting faculty, it could be possible to collaborate. So this is just the things which I have done so far, and my last 1 year publications I have done in elsewhere and Springer. 5 book chapters I have, and I have 1 edited as a lead editor. I have edited CRC book, and 1 I have authored 1 book from NOVA. So this is what I have been working, and I would like to explore the possibility if I could be a part of any of the research group. My expertise is based on the marine derived fungi, which is we can say untapped potential so far explored. Thank you so much.
Thank you, Dr. Anjana, for your presentation, and we can conclude today's section. And I thank all the delegates for your valuable support and presentation in these today's sessions. And I thank everyone from Mahatma Gandhi University to organize this session and support us in this session. So tomorrow also we have sessions and it will start on 8:30 onwards. So thank you all and have a good evening.
Thank you so much.
A wonderful evening. Thank you. Make use of all the contacts for international and domestic cooperation and collaboration. All the best. See you tomorrow at 9 o'clock. Thank you.
Thank you. Thank you, and see you tomorrow.
See you tomorrow.
Bye-bye.
Bye-bye.